If you use Excel's FX button to help you enter Excel functions, you will appreciate @Risk's Insert Function tool. If you don't use Excel's FX button, here's how it works. It basically walks you through the process of entering a function in an Excel formula, prompting you for the required and optional arguments. For example, you can use it to help you enter the PMT function, payment function, to calculate the monthly payment on a loan. Assuming the monthly interest rate is 0.5%, the term of the loan is 36 months, and the loan amount is $20,000. You first click the FX button to the left of the formula bar, and you choose PMT from the financial group. This leads to a dialog box, which you fill in as shown here. 0.5% means 0.005, 36 months, minus $20,000. Note that the loan amount is entered as a negative number because you owe it. Also, note how Excel provides a brief explanation for each argument and that non-bold-faced arguments are optional. When you click OK, the correct formula is automatically entered for you. The result is 608.44. Obviously, there are other ways to enter Excel functions, and unless you feel the need to use the FX interface, you will probably favor more direct and quicker ways of entering functions, particularly those you are familiar with. The Insert Function drop-down on the @Risk ribbon is very similar. It provides a list of all at-risk functions broken down by category. The category list is shown here. You can select any of the functions from any category to bring up a dialog box, much like Excel's, where the function's arguments are listed and you can simply fill them in. As with Excel, there are other ways to enter these functions that you might prefer. For example, to enter a distribution function such as risk binomial, you might prefer to enter it manually, or you might prefer to go through the Define Distributions interface. This is entirely up to you. To give you a sense of the possibilities, I will walk you through an exercise on the worksheet shown here. First, select cell B1 and choose Risk Normal from the Common or Continuous category of the distribution functions. Enter 100 for the mean and 10 for the standard deviation, and click OK. There's the Risk Normal function. Second, choose cell B2 and choose Risk Theo X to P from the Theoretical category of the statistical functions. Point to cell B1 as the data source and enter 90 as the X value, and click OK. The result is about 0.159, the probability of being less than 90. Number 3, select cell B3 and choose Risk X to P from the Simulation Result category of the statistical functions. Point to cell B1 as the data source, enter 90 again as the target value, leave the next box blank, and click OK. You will get an error or a wrong value in cell B3 because this function isn't defined until a simulation is run. You can fix this by running a simulation. There's the result. Now you get an estimate of the probability of being less than 90, which should be close to the theoretical value in cell B2. Next, enter the formula equals square root of B1 in cell B5. You can assume that this represents a measure of quality, based on the random value in cell B1. Then, with cell B5 selected, click the Add Output button, click its FX button, click the Six Sigma tab, and fill in the resulting dialog box as shown here. FX button, Six Sigma, make this 8.5, 11.5, 10. The LSL and USL values are specification limits. Any items with values beyond this range will be considered defective. Note that the risk output function now includes the property function risk Six Sigma. Finally, select cell B6 and choose the risk DPM function from the Six Sigma category of the statistical functions. DPM stands for defectives per million. Point to cell B5 as the data source and leave the other two boxes blank and click OK. Again, you will get an error because this function isn't defined until a simulation is run. To fix it, run a simulation. You get the value 4,000, meaning that with this normal process and these specification limits, 4,000 items out of every 1 million items produced will be defective. Again, this exercise has demonstrated only a few of the things you can do from the insert function dropdown. Also, you might prefer to enter some or all of these functions in different ways, such as through the Define Distributions window. But if nothing else, the insert function dropdown provides a quick and handy way of seeing all available at-risk functions, especially those you are less familiar with. The small Simulation Settings button on the At-Risk ribbon opens a dialog box where you can change a lot of settings for the current simulation. You probably won't need to change any of these settings except for the number of iterations and possibly the number of simulations. And you don't need the dialog box for these, but you ought to be aware of the possibilities. The General tab provides an alternative way to specify the number of iterations and the number of simulations. It also lets you enable multiple CPU cores in a single machine to speed up simulations. You are allowed 2 CPUs in the professional version and an unlimited number in the industrial version. This setting is enabled by default. The bottom section allows you to display either random or static values in the uncertain input cells. This setting can be changed by toggling the dice button, or it can be changed here. You might find it disconcerting to have, quote, random values that don't change when you press the F9 key, in which case you can choose the random values setting. On the other hand, the static value setting can be very useful when you want to see what the results would be in a deterministic setting, that is, where the uncertainty is removed. Note that the drop-down for static values allows 4 possibilities: expected values, true expected values, modes, or percentiles, where you could choose the percentage. The difference between expected values and true expected values is relevant only for discrete inputs. In this case, the true expected value could be a value like 13.3. In contrast, the expected value setting would round this to 13. The idea is that if only integer values make sense, a value like 13.3 shouldn't be shown. In any case, the random static setting has absolutely no effect when you actually run the simulation. In the View tab, the top section provides options on what you see when you run a simulation. For example, if you don't want a chart to pop up automatically, you can choose None. This is equivalent to toggling the button next to the dice button to white. Alternatively, if you select Demo Mode, This is equivalent to toggling the button to the left of the Start Simulation button to orange. The Show Results Summary Window option opens the summary window instead of the Browse Results window when the simulation runs. The bottom section of the View tab provides other viewing options, which should be self-explanatory. The Random Numbers section of the Sampling tab contains some important settings. First, the sampling type is either Latin hypercube or Monte Carlo. Given that spreadsheet simulation is often called Monte Carlo simulation, you might expect Monte Carlo to be the preferred sampling type, but it isn't. For technical reasons, Latin hypercube is much more accurate. It is the default at-risk setting, so unless you have a very good reason, you shouldn't change it. The generator is the method used to generate uniformly distributed random numbers between 0 and 1, the building blocks for random numbers from any distribution. Researchers have developed many random number generators, and any in the generator list should work well. The default Mersenne twister shown here has good statistical properties and is a good choice. The initial seed can be fixed at any positive integer value, or it can be random. The fixed setting is a good one if you want to be able to replicate your results at a later time. But if you want different results each time you run the simulation, you should use the random option. Finally, you should usually keep the all use same seed for the multiple simulation setting. This provides a fair comparison when you run multiple simulations with a risk SimTable function. The other options in the bottom section of the Sampling tab are more advanced, and you can read about them in At-Risk's help. You will probably want to keep them at their default settings. Similarly, the settings in the Macros and Convergence tabs are more advanced, and you probably won't need to change any of the default settings. Just be aware that it is possible, and sometimes very useful, to write macros that perform various tasks before, during, or after a simulation run. The options in the Macro tab let you implement this. Of course, you have to write the macros in Excel's VBA, Visual Basic for Applications, macro language. Finally, keep in mind that these settings are for the current simulation only. If you want to make more permanent changes to the look and feel of At-Risk, you should change Application Settings, found under the Utilities dropdown. This brief video discusses a very welcome color coding feature that was added toward the end of the development process for At-Risk 6.0. This feature is found in the Help group of the At-Risk ribbon. It allows you to specify colors for cells that contain at-risk input functions, at-risk output functions, at-risk statistical functions, and at-risk optimization variables, that is, adjustable cells for risk optimizer models. The Color At-Risk Function Cells option is a toggle. If it is checked so that it appears orange, cells are colored for all open at-risk models. The cells are also automatically colored then when you open a file that contains an at-risk model. The Specify Colors option opens the following dialog box, where you can accept the default coloring scheme or change it as you like. As an example, the at-risk model you see here has its own color coding, specified by a user before these new color coding options were available. At this point, the Color At-Risk Function Cells toggle is off. However, by turning it on, the model changes as you see here. And this is now orange, reminding you that it is turned on. The powerful Risk SimTable function allows you to run a separate simulation for a list of values in some cell. This cell often corresponds to a decision variable, such as an order quantity, but it could contain an interest rate, a starting date for a project, a response rate to a new product, or any other quantity you would like to vary. In any such case, you supply a list of possible values you would like to try as arguments to a risk SimTable function. If the list is stored in a cell range, you reference this range. If you type the list manually, you need to include the list in curly brackets. Here are two possibilities. I'll reference a range. Or I will type the values inside curly brackets. Note that the first value is always shown. The model shown here, adapted from one of the at-risk example files, illustrates a possible use of the risk SimTable function. A company is introducing a new product, and the model estimates the NPV of cash flows from the product over a 10-year horizon. A key input to the model is whether a competitor enters the market at the beginning of year 1. This input is either 0 or 1, as shown in cell C8, and this is determined by the probability of entry in cell E8. The company would like to try 3 very different values, 0.1, 0.5, and 0.9, for this probability of entry to see their effect on NPV. To do this, you enter the risk SimTable function in cell E8 and specify its arguments as the list to the right. Again, it shows the first member of the list. Then you set the number of simulations to 3. Because you want at risk to run 3 separate simulations, one for each of these probabilities. If the number of iterations is set to 5,000, as it is here, at risk will run each of the 3 simulations for 5,000 iterations. Better yet, it will use the same random numbers for each of the simulations. This provides a fair comparison of the results for the 3 probabilities. By using the same random numbers, they all face the same scenarios. Now I will run the simulation. You can browse an output for any of the simulations. By default, you will see the results for the first simulation. But you can click the button with the pound sign to select any other simulation. Alternatively, if you'd like to use at-risk statistical functions such as risk mean, you can append a last argument, the simulation index, to any of them. In this case, the index is 1, 2, or 3. As you gain more experience with at-risk, you will probably see more and more uses for the risk SimTable function. For example, you might want to see how sensitive the distribution of some output is to the shape of some input distribution. The model shown here illustrates one such possibility. The demand in cell B15 drives the profit in cell F15, but the company isn't sure whether to use a triangular or normal demand distribution. With a risk SimTable function in cell B11, using the indexes 1 and 2, they can try both. The logic is then captured in the demand cell with an if function. If the index is 1, use risk triangle. Otherwise, use risk normal. The results from running to the 2 simulations are captured below with at-risk statistical functions, using last arguments 1 and 2. By now you should appreciate how useful the risk SimTable function can be. However, what happens when you enter it in 2 or more cells, each with its own list of possible values that you would like to try? You might expect this to run a separate simulation for each combination of values. For example, if there are 4 possible values for the first cell and 3 for the second, you might expect this to run 4 times 3 or 12 simulations. However, it turns out that this is not the behavior you will get. Fortunately, there are a couple of ways to get at risk to run 12 simulations, one for each combination of values. The worksheet you see here illustrates these methods. You should first list the combinations of values you want to test, as in rows 4 and 5. In this case, each of 4 mean values will be paired with each of 3 standard deviation values. So you set the number of simulations to 12. In general, this table of combinations can have any number of rows, 1 per variable, and any number of columns, 1 per combination of values. The model itself doesn't do much. The input and output are each a normally distributed random value with mean and standard deviation equal to one of the combinations. At-risk statistical functions are used in rows 19 and 20 to verify that risk SimTable is working properly. In the first method, you enter a separate risk SimTable function for each variable in cells C8 and C9 with argument equal to the entire corresponding row of the table. The means, and I can copy that down for the standard deviations. It would be tempting to list each possible mean only once and each possible standard deviation only once, as indicated in the red cells. However, this would be incorrect. It would not give you the results you would expect. In general, if you set the number of simulations to a number such as 12, then when at-risk runs simulation number 4, say, it uses the 4th value in each risk SimTable function it finds. If a risk SimTable function has fewer than 12 values, the corresponding simulations return errors. For example, if you have a risk SimTable function with a list of only 10 values, and you set the number of simulations to 12, the 11th and 12th simulations will return errors. On the other hand, if you have a risk SimTable function with a list of 14 values, and you set the number of simulations to 12, the 13th and 14th values will be ignored. They will never be used. In the current model, the risk SimTable functions in cells C8 and C9 each have lists of length 12. So it is correct to set the number of simulations to 12. Now I will run the simulation. As you can see from the results below in rows 19 and 20, everything is working as it should. The means and standard deviations match up to the values up here. An alternative method you might prefer is to use a single risk SimTable function with a simulation index going from 1 to 12. Then you use lookups to find the appropriate parameters. For example, in the version shown here, I will enter a risk SimTable function in cell J7 using the indexes 1 to 12. I'll highlight the indexes. As usual, it shows the first value. And then I will capture the appropriate mean and standard deviation in cells C8 and C9 with HLOOKUP functions. Looks up the index in this table and finds it in the second row. For the standard deviation, it will find it in the third row. Now I will run the simulation again. As you can see, you get the same basic results as before. You might prefer this lookup version, but it does take more computing time, which could be an issue on more complex simulation models. The reason is that it is looking up values frequently in the lookup tables.